Good morning from Vancouver, everybody. It's a rainy day, not exactly great for astronomy, but it's a good time to be online. I'll be your host today. I'm Scott McGillivray. I'm also I hold several roles with the RASC Vancouver Center, and yeah, I'm also going to be one of the presenters today. Today we've got Aaron Boley, Michelle Kunamoto, and Jess McIver joining us. All of them are doctorates, and a PhD candidate is Michelle at the University of British Columbia. I'm sure most of you know who they are already. So yeah, let's get into it with our first speaker. We have Dr. Aaron Boley. He's an associate professor of astronomy and physics at UBC and Canada Research Chair in planetary astronomy. Over to you, Aaron.
All right, well, thank you very much, Scott, and thank you to everybody for joining. So what I want to talk about today is how we are changing our use of space and some of the considerations into a kind of a new era of astro-environmentalism. And for space users such as ourselves, who also not just use space through our cell phones or banking transactions, when we go to the grocery store, when we use the internet, like so many other people, but we also use space in the sense of appreciating it, looking at the stars, using our telescopes, taking images, and so forth. There are many different complex considerations of trying to be able to use space while also preserving what we have. And because I'm a physicist, one of the first things I want to talk about, are cows. So if we have a pasture and we have, cattle on that pasture, this is a classic example of a commons. This would be a local commons, and the idea is it's a shared resource. And there is a well-recognized problem known as the tragedy of the commons. And the idea here is that so you have multiple users of this one resource, and maybe you have a bunch of cows, and you realize that you can add one more cow to that pasture, which it can be sustained just fine without having too much risk. But every other person who's using that resource will come to the same conclusion, that they could increase their economic benefit by having one more cow. And so everyone does that. And this can lead to a crash of the commons, which is known as the tragedy of the commons. And in fact, this is a fairly old idea and is popularized by Hardin in 1968. And one of the interesting things about this particular issue is that it doesn't have a technical solution. Because if you have technology that comes in that might be able to maximize the way you use that resource, then you can easily just fit one more kind of cow in to take up that extra benefit. At least that's kind of one of the viewpoints here. And Hardin went so far as to have this fairly amazing quote where saying, "The ruin is the destination toward which all men rush, each pursuing his own best interests in a society that believes in the freedom of the commons. Freedom in a commons brings ruin to all." And you can imagine this like dark music playing in the background as one's reading that. But the issue here is that people are going to act selfishly, and as a result, they're going to destroy what they're using. That's one particular take. Now, Hardin said the only way you can kind of get out of this is have some type of monolithic actor, such as a government, come in and set down regulations. Now, it turns out that that bleak picture that Hardin painted is not really correct in a general sense, although it is an issue when we get to global commons, which we'll talk about next. If you have a local region, though, the resource users, it is within their best interest to maintain the commons. So while at first, kind of this Hardin picture will play out, people will recognize the destruction, and then they will pull together and have kind of this grassroots effort to control the problem. and they will be able to self-regulate. And there are many instances that Ostrom pointed out that show how local organization can in fact provide better management of a local resource than a monolithic government coming in to tell you what to do. And so there's this picture here of the commons versus time. You have this initial fall, which is now known as the tragedy of the commons. And then if people are able to adjust and regulate themselves accordingly, you could have this resilience of the commons. You could have it bounce back. If you can't regulate it accordingly, then you could have a total collapse. So if we go back to the pasture picture, the pasture picture was very much an imperfect example, because while there are times where the overgrazing has led to collapse of pastures, but there are also plenty of examples in which people have been able to manage pastures for hundreds of years without an actual problem. Where it gets tricky is when you start talking about international commons, such as the high seas or space, Antarctica. You have now a region in which there is not any type of monolithic kind of organization that could come in to put regulation from the Hardin point of view. So you kind of are in this grassroots regulation, but it's on this international stage. And it really changes the dynamics, because you do not have kind of a very localized group of resource users. And to get it wrong can crash the entire global commons. So if you have a very local commons and you get something wrong in a pasture, you move to the next pasture. If you get something wrong by destroying your oceans, you don't move to another ocean. So space. So space is a region that does not have a particularly good definition of what exactly it is. Many people take the view that it is a type of global commons, but there are nations who reject the idea that space is in fact a global commons. And this went back to the very start of the space age itself. And so many countries were exerting that their sovereignty just extended upward. It's just like airspace is within the jurisdiction of a given country. They just said, well, it just keeps going upward and our jurisdiction extends into space. Well, Sputnik 1 completely settled that debate, because the USSR put up a satellite, and what are you going to do about it? So a satellite was able to just orbit the Earth, and that immediately demonstrated that any given country could not dictate what happens in space alone. So we have a commons. But not everyone takes that view. In fact, the United States administration on April 6th just put out an executive order that explicitly rejected the concept of space being a global commons. And one of the tricky parts is, if you're not going to say it's a global commons, it is definitely a region that's beyond the jurisdiction of an individual state. And that's pretty well set within kind of the international use of space. All right, so how have we managed space as a resource so far? Well, this is a cumulative plot of the objects in space that we are able to track. So these are objects that are 10 centimeters or larger. We have them in a catalog. You can in principle observe them and reacquire them at a later date. So the red, that's the accumulation of rocket bodies, these school buses that are just orbiting the Earth as a function of time. The orange is the payload or satellites. That includes both active and defunct satellites. So there are about half of those that you see by 2020 are derelict spacecraft. Now, the one thing that's going to be of interest for most of this talk is the green curve, and that's the debris. This is orbital debris. And there are many reasons for that debris to be present. You'll notice that it goes up and it goes down. And the reason why it goes up is because you have debris generating events, and there are a number of different things that can cause debris generating events. And it goes down because you have things like atmospheric drag. Even though you're up at high altitudes, there's enough gas drag up there to slowly bring things down. So you have this evolution, but overall the trend is up. And you see some pretty spectacular changes in the distribution. And before we get to those, let's talk a little bit about why you have the debris in the first place. So part of the debris is up there just because of operations. So the reason why those giant rocket bodies are up in orbit is because it takes fuel, and therefore it's expensive to deorbit them. And so for most missions, the simplest thing to do is to leave the rocket body up there. And because they have so much mass, and depending on exactly what their orbits are, they tend to stay up there because atmospheric drag takes a long time to bring them down. Now, you have some degree of operational generation of debris, and that's actually a very small amount. That's not really shown here on this particular pie chart. But what is shown is that not quite half, just a little short of half of all of the breakups comes from propulsion. So almost half of the debris that you see on that plot comes from things exploding because of unspent fuel. About 4% comes from batteries exploding, just leftover batteries. You have accidents, accidental collisions, and these are accidental collisions that we know of, and I'm going to show you an example of that. Unfortunately, about a quarter of the debris we see up there is totally deliberate. So something that's known as counter space capabilities. So they've purposefully blown something up. Then there's another quarter that's just totally unknown. And it's these are called the anomalous events. It's suspected that this has something to do with collisions with other debris, possibly collisions with meteoroid, but it's just simply of an unknown origin. It could easily be unspent fuel that's exploded. So going back to this chart, we can see that there's this jump in 2007, and that was a Chinese anti-satellite test. And so many countries had, well, the United States and the USSR had previously done anti-satellite testing where they purposefully destroyed a satellite. This particular one was extremely bad because of the amount of debris it generated and where it was located. So let's go ahead and take a look at this. There we go. So this is an animation that tries to depict what that may have looked like. And so as a weather satellite, a Chinese weather satellite went over China, a missile was launched from China that destroyed the spacecraft at about 750 or to 800 kilometers in altitude. It generated a debris field, and some of that debris actually went at orbits where the ISS went through. So it endangered then the astronaut program. Then in 2009, there was the first major accidental collision. And this was between Iridium 33, which was an active satellite, and Cosmos 2251, which was a defunct USSR satellite. And so if we go ahead and play this, here's the Iridium constellation. And then, I believe it was February 9th, or maybe February 10th, you had those two satellites slam into each other and created a tremendous debris field. And so space is big. Space is really, really big. But if you wait long enough, things are going to collide. And that's not hypothetical, it's happened. And the majority of the debris is still up there. Now here's one of the major issues anytime you have a fragmentation event, or anytime you have, particularly if you have a satellite-satellite collision. you have the mass of some body, and it's not quite as simple as this, but say the mass is going to go as the diameter cubed. Your cross section is going to d squared. And so you can imagine that if I take one particular object, say a satellite, and I split it up into a whole bunch of other objects, now I have many more BBs that can collide with other satellites. Another way to think about that is your total collisional cross section actually goes up as a result of that one collision. And so now the probability that you'll have another collision within a set amount of time also goes up. This is known as the Kessler Syndrome. And right now, the satellite population is not dominated, or the fragmentation events in the satellite population is not dominated by debris. But eventually it will be. In other words, a piece of debris is going to slam into another satellite, which is going to cause much more debris, and you're going to have a cascade. And there's been some considerable work on this. This goes back to 2008, so this was after the Chinese ASAT test, but before the 2009 Iridium and Cosmos disaster. And at that time, they demonstrated through calculations that if you have regular launches at the 2008 level, and 90% post-mission disposal with no debris mitigation, you would develop the red curve, which means you're seeing runaway growth in the debris field. Now, notice the time scale that's involved here. You really start to see the change in the debris around 2050, and then you have a clear runaway by 2200 or so. And so, from a policy perspective, and for any type of environmental type of action, this is a hard concept. Space, even in the satellite domain, has timescales that are much longer than what humans typically think about. And so if you're trying to manage something well as a resource, and space orbital slots, that's a resource, we have to try to think well ahead. And that's just really hard. Now, another thing this plot shows, it gives some hope that if you have things like active debris removal, so you go up and you take down those defunct satellites, then you could do a good job at maintaining the orbital space. But that's expensive, and there are legal problems with that I can't really get into. We see multiple issues with the debris that's up there. And so the International Space Station, is constantly getting hit with debris. Luckily, there's been no major issues. Solar panels have been destroyed. The bottom left there, that's the WIFPIC 2 radiator from HST that was brought back down. And that thing has just a bunch of little debris strikes all over it. The final thing that I really want to show you here, and this is going to come into, we're going to talk about it a bit more before time runs out. We have new space. So this concept of new space is just a way of talking about how our use and our integration with space is changing. At the very beginning, I talked about how we are space users, and we are space users in ways that most people don't even think about. They don't think about how financial transactions are in fact tied to space, because you need the accurate clocks that are set by GPS. We don't think about how our coordinate system actually has changed as a result of space. So if you go to Greenwich, the prime meridian is 100 meters or so away from the historical prime meridian. And that's because satellites have caused a slight change in our coordinate system. There are all these little changes that have affected us, and some are actually quite substantial. But all that kind of gets folded into this idea of new space. But I think one way, kind of as a physicist and an astronomer, the way I like to think of new space is there's a derivative change. So you have the slope of the curve in the way that we were putting satellites into orbit. And then around 2015 or so, you start to see this ramp up. And now this is really starting to jump forward. Why is that? We have the rise of our mega constellations. Starlink is an example of one of these mega constellations. And SpaceX has been so successful that it is now launching 60 satellites at a time. And that's what you're seeing here. You're seeing 60 Starlink satellites being launched at one go. And so that's why, if we go back to this previous slide, the rate at which we're putting rocket bodies into orbit has stayed roughly the same, but the way we've been putting payloads into orbit has been increasing quite a bit. And that's because we're getting better and better at putting multiple satellites in any one go. Now, we're talking about how debris and satellites are getting placed into orbit, but another very important component of the puzzle is that you don't put everything kind of uniformly spread out. And this is part of the issue. Satellites have missions, and in order to achieve those missions, they need certain orbital slots. And so certain orbital slots are much more crowded than others. And so what you're seeing here is a number density of satellites and debris and rocket bodies as a function of altitude. The blue curve is the track debris. This is debris that's just 10 centimeters or so or larger in diameter. There's much more debris when you go to smaller sizes. It's roughly a factor of 30 to 40, depending on estimates, if you go down to size scales of 1 centimeter. But a large portion of this debris is from the Iridium Cosmos disaster and the Chinese ASAT test. And that's what causes this big spike of debris between 750 and about 900 kilometers. These spikes that you see in green are due to preferred locations of placing satellites for various missions. And so space can get pretty crowded. And this increases the probability of a collision risk if you're not able to do proper avoidance maneuvers and so forth. And this is going to become extremely important, again, when we talk about the mega constellations, because we're going to be packing a lot of satellites into those locations, and the spikes that you see there in satellites are going to go way up. We're going to have very high densities that are it's going to be critical that you have station keeping capabilities within the satellites. And places like Starlink or constellations like Starlink are planning to do just that. Now, where I would like to end this talk is to talk about other effects though. So that's just an operation, and that's kind of a problem that's going to need to be solved in the management of space as a resource. But there's another perspective, and that's this natural and cultural heritage, preservation of the night sky. Many of you have probably already seen this. Oops, why is that not showing? There we go. You've probably seen the Starlink trails go across the sky, or at least have seen videos of the Starlink trails. So this is one of the first sets of 60 Starlink satellites that have been placed out. Now, these are particularly bright because they were recently launched. That's why they're also in this very tight trail. But even as they go up to their higher altitude, they're still going to be interfering with imaging and so forth with our telescopes. To what degree? Well, you could take just the Starlink satellites as filed, and we could ask for any given latitude, for any given season, how many satellites will be in our local sky and be sunlit. Now, that doesn't mean that they're going to be particularly bright. It just means that light is shining on them from the sun and they're in our sky. And the way the constellations are designed, there's actually going to be these large peaks around 40 and minus 40 latitudes. If we further constrain this to be the number of satellites that are above 30 degrees altitude in our local sky, then actually the peak is right around us. So we're going to actually, during the summer, we'll be able to see satellites in the sky, you know, at a fairly constant rate, where there's going to be about, you know, at least for just Starlink, there will be, you know, between 80 and 90 satellites. And if we keep going forward, this is an animation that's put together by AGI that shows over time the growth of mega constellations. So that started in 2017, and this isn't showing the existing satellites. This is just showing the constellations as planned. A lot of the SpaceX constellations, that's already going up, so that's already happening. This year, there are many more satellites that are already planned. And we should take at face value that many of these constellations will go up. Not all of them, but many of them will. But it shows the ambition that we have kind of as a society. And this is going to create global connectivity, which we've never seen before. So this is going to be something that's going to be really hard for us to push back on, because it's going to be adding search and rescue capabilities like we've never seen, connecting communities that are otherwise isolated. So in many respects, there are parts of it that we shouldn't push back on, but there are parts of it that are just a natural heritage of the sky part, and it's going to be affecting it. So what I showed you previously, that was just a map for the Starlink satellites. What you have here in the next decade would be a 10-fold increase in the number of satellites in our sky. And there are many different parts, and I don't have time to go into it. So I painted perhaps a bleak picture. So one of the things that I do want to make sure is clear to everyone is that there are good things that are happening. So one, everyone is in fact fairly afraid of orbital debris, because it could mean the loss of space assets. And so people are taking measures to try to manage debris. There are guidelines that are being placed. These are very soft guidelines, where individual nations can then choose to act on those guidelines or not, but to try to limit the amount of debris. And there is investment in debris removal technology, but that's coming along slowly. But I think one of the important things, and the reason why I decided here to talk about this, is that we need to raise public awareness of this issue. And if we're able to do that, then we can also start finding solutions to these problems. And so I'm going to skip ahead to this one last slide and just say, you know, space environmental stewardship is not a purely technical issue. And so we need to be involved with managing space as a resource. And I'll go ahead and stop there.
All right, here, let me come back in. Thank you very much, Aaron. I think we have time for one question if anybody wants to ask one. Otherwise, we can you can put your questions down in either the Q&A section or the chat section. And
I can also show one more movie if no one has a question.
I would love to see it, but I could also ask a question.
Okay, maybe we can do both.
So I heard with the Starlink satellites that going forward, Elon Musk is going to put an anti-reflective coating on them so they won't be so bright. What are your thoughts on that?
So, okay, so I have a couple thoughts on that. So one, there's the DarkSat that was tested, okay? And there are multiple issues with this. So from one standpoint, if you just make it dark, one, it's really hard to make it really dark because it needs to be really dark. But then if you make it really, really dark, that means it's absorbing more radiation. And so it's heating up. Problems with that, satellites are designed to take certain thermal stresses. And if you take a satellite that's designed to take a certain thermal stress and you drastically change the amount of heat that it absorbs, then that can stress the satellite, shorten its life. It could cause batteries to explode, for example. So that's problematic. Another issue is, you know, as astronomers, we know that energy is still there. And so it's just being re-radiated in thermal. And so you solve the problem for optical, if you look at it the most optimistic way possible, and then you mess it up for the infrared. And there's another issue with it, and that is with all these satellites, we're thinking about, you know, them being able to see them, but they also block things. So they're causing occultations. And so if you have things like the TAOS-2 survey, or you have any type of occultation coordination that has very high frequency observations, then satellites can be problematic. For long integrations, the occultations aren't going to matter because these satellites are moving at 200 arc seconds per second or so. But you know, if you're doing things that have very high frequency searches, then it will in fact affect everything. Now, they're looking at different things to do too, such as shading, to make sure that when light gets reflected, it doesn't get reflected back to Earth and so forth. And that might help. But so far, the solutions have been, you know, reductions by a factor of 2, which means, you know, maybe it will affect what people see in the night sky, but it won't affect really what our telescopes see.
Excellent. Well, I'm hoping for the best. I'm not optimistic, but that's just my opinion. So.
I mean, Starlink is going up, but with these new constellations that are coming, we do have the ability to try to put some type of sensible restrictions on the use of space resource slots, so that we can have the connectivity that the mega constellations want to have without just letting absolutely everyone put assets up, because there is a commons issue here. It is a finite resource.
All right. Well, thank you very much, Aaron. Always a pleasure hearing from you, and hope to see a lot more of you in the future at the Vancouver events.
I'd be glad to.